Welcome to Orbit Observer. Settle in. There is nothing you need to do for the next little while except breathe and let the day go quiet and drift out here with me to a small burned world spinning close to a fire. You can close your eyes. You don't have to follow every word. This is not a lecture, and there will be no test in the morning. Only a slow walk around a planet you have probably never really looked at, told softly enough that you can fall asleep somewhere in the middle of it and lose nothing at all. If you wake at 3 in the morning, the story will still be here. If you never hear the end tonight, that is completely fine. That is, in fact, the whole idea. Let me tell you where we're going. There is a planet, the innermost one. The one that hugs the sun so tightly that from Earth we almost never see it, except as a shy point of light low over the horizon just after sunset or just before dawn. Mercury. And here is the thing about Mercury that almost no one tells you. The thing I want to walk you slowly into tonight, because it is one of the strangest quiet facts in the entire solar system. This planet is shrinking, not in the poetic sense, not as a figure of speech. The actual physical body of Mercury, the whole ball of iron and rock, has been getting smaller. Its radius, the distance from its dead center out to its surface, has contracted by something on the order of 5 to 7 kilometers. The whole planet has drawn itself inward, tightened, crumpled, the way something dries and pulls in on itself when the warmth leaves it. And the marks of that shrinking are written all over its face in cliffs taller than almost anything on Earth. Cliffs that, as far as we can tell, may still be forming right now. Tonight, while you lie here in the dark. I know. 5 to 7 kilometers doesn't sound like much when you say it out loud against the scale of a planet. Mercury is a world thousands of kilometers across. Losing a few kilometers of radius is like a person losing a fraction of their height. But hold on to this, because it's where the wonder lives. To lose that from your radius, the entire skin of you has to shrink to fit. The whole outer surface, every rock and ridge and crater floor, has to crowd together into a smaller space. And a planet's crust is not soft, it's solid stone. Solid stone does not simply squeeze politely inward. When you force a rigid shell to cover a smaller ball, something has to give. The stone has to break and buckle, and one slab of crust has to ride up and over its neighbor. And the result is a cliff, a wall of rock shoved into the sky by the slow, patient, unstoppable pressure of a planet closing in on itself. So let me give you the picture the way I'd want it given to me if I were the one drifting off. Imagine an apple left too long in a bowl on the counter. You've seen this. Over days and weeks the fruit inside dries out, loses its water, shrinks a little. But the skin doesn't shrink, or doesn't shrink at the same rate, and so the skin has too much surface for the smaller fruit beneath it, and it puckers, wrinkles, folds into those soft brown ridges. A raisin is the same story finished, a grape that lost its water and pulled inward until its skin had nowhere to go but into wrinkles. That, almost exactly, is what has happened to Mercury. The inside cooled and pulled in. The skin, the crust, had too much surface for the smaller world beneath it, and so it wrinkled. Except Mercury's wrinkles are made of bedrock, and they stand 2, sometimes 3 kilometers tall, and they run for hundreds of kilometers across the grey plains. Wrinkles you could see from space. Wrinkles that took a planet to make. Scientists have a name for these wrinkle cliffs, and it's a gentle enough name to say in the dark. They call them Lobate Scarps. A scarp is just a cliff, a step in the land where one level drops away to a lower one. Lobate means it curves, it has rounded lobes, it snakes and bows across the surface rather than running dead straight. So, lobate scarps. Curving cliffs, and underneath that quiet name is a violent little truth about how they formed. Because each one of these is what a geologist would call a thrust fault. Picture two hands laid flat on a table, fingertips touching. Now push them slowly together. They can't pass through each other, so one hand has to climb up over the other. One rides up while the other slides beneath. That climbing edge, lifted into the air by the squeeze, is the cliff. That's a thrust fault. Horizontal pressure from the whole planet compressing turned into a vertical wall. The land was pushed from the sides until it had nowhere left to go but up. Some of these cliffs have names, and I like saying them slowly because they sound like places out of an old sea chart. Discovery Rupes. Rupes is simply the word planetary scientists use for these long cliff scarps, borrowed from Latin, and Discovery Rupes runs for roughly 650 kilometers across Mercury's surface. 650 kilometers. That's a single unbroken cliff, longer than most countries are wide, a wall of shoved-up crust marching across the plains, rising as much as a couple of kilometers along its length. There's Enterprise Rupes, one of the largest of them all, a vast contractional feature that dwarfs anything comparable on Earth. There's Beagle Rupes and Carnegie Rupes, each one a scar, each one a place where the crust broke and rode up under the pressure of a shrinking world. Some of these named cliffs are so large that if you could stand at their base and look up, the top edge would be lost somewhere far above you, a lip of grey stone hanging against a black sky, and you would have no idea, standing there, that the reason it exists is that the entire planet under your feet is very slowly crushing itself smaller. Now let me fold something in here, quietly, before we go deeper, because I would love to know this about you. Tell me where in the world you are watching from tonight. Leave it in the comments. Just the place, the city, or the country. The corner of the earth where you're lying in the dark, listening to a voice talk about a shrinking planet. I read them, and there is something I find genuinely lovely about a scatter of names from everywhere on one world, all drifting off to sleep over the story of another. And if you're new here, if you've wandered in from somewhere and this slow kind of thing is what you needed, you can subscribe, and more nights like this will find their way to you. That's all. No hurry, let's go back down to the surface. Because here is the part that made scientists lean closer. For a long time, the assumption was that all of this happened long ago. That Mercury shrank early in its life, in the first billion years or so, when it was young and hot and cooling fast, and that the cliffs were ancient monuments to a process that had long since finished, a planet that had done its shrinking and gone still, a closed book. And you could understand why anyone would think that. Mercury is small, and small things cool quickly. A cup of coffee goes cold long before the whole ocean does. A small planet should have shed its heat billions of years ago, frozen solid to the core, and stopped changing entirely, becoming what it looks like at first glance. A dead grey ball, pocked with craters, a slightly larger cousin of our own moon. But then people looked more carefully at the smallest of the cliffs. Not the great 600-kilometre giants, but the little ones. The short, crisp fault scarps, only a few kilometres long, sitting here and there across the plains, and they noticed something about them that changed the whole picture. These small scarps were fresh. They were sharp-edged, unworn, undamaged, and on a world like Mercury, freshness is a clock, because Mercury has no wind, no rain, no rivers, no weather of any kind to soften a landscape. The only thing that wears down the surface out there is the endless slow rain of tiny impacts, micrometeorites and small strikes chipping away over the ages, blurring sharp features into soft ones the way 1,000 years of footsteps round the edge of a stone step. A very old feature on Mercury should be battered, cratered, degraded, its edges gone soft. But these small scarps were crisp, their edges were sharp, they showed almost none of that wear. Which means, unless we've misunderstood something, they are young. Geologically young. Made not billions of years ago, but recently, in the last little while of the planet's life. And if the small scarps are still fresh, then the process that makes them, the shrinking, the crushing, the shoving up of crust, may not be finished at all. It may still be happening. That work came out in 2016 from a team led by a scientist named Waters and colleagues, published in the journal Nature Geoscience, and the phrase that came out of it is one worth carrying off to sleep with you. They described Mercury as tectonically alive. Alive, not a dead cinder, not a finished world, but a planet still moving, still adjusting, still cracking its crust and lifting new cliffs as its insides go on cooling. Now, I want to be honest with you the way I'd want someone to be honest with me, because the honesty is part of what makes it restful rather than breathless. No one has stood on Mercury and watched a cliff grow. No one has felt the ground move there. This is inference, careful inference, built from the sharpness of edges and the logic of what could and couldn't survive on a weatherless world for billions of years. It is a strong argument, but it is an argument, a reading of clues, not a filmed event. And still, when you sit with it, the idea is quietly staggering. That somewhere out there, right now, on a planet you cannot see from your window, the ground may be lifting, slab riding over slab, a new cliff rising a whisper at a time, in perfect silence, in the dark, while the closest planet to the sun goes on very slowly, making itself smaller. There's a mission I'll tell you all about later near the end, when hopefully you're already half gone into sleep. A spacecraft built in part to look for exactly this, to search Mercury for signs of present-day fault activity and even for what you might call Mercury quakes, tremors from the crust still shifting. Because if the ground is really moving out there, if the planet is really still crushing itself, then it would shake, faintly, the way the Earth shakes when its crust adjusts. And to catch that would be to catch a planet in the act of shrinking. But that's a story for later. Hold it as a loose thread. We'll come back and pull it. For now, I want to take you underneath the cliffs, down past the crust, into the reason all of this is happening. Because the shrinking is not the story. The shrinking is a symptom. And once you understand the cause, everything strange about Mercury, and there is so much that is strange about Mercury, starts to line up into a single, quiet argument. So let's go down. Why does a planet shrink? It comes down to heat, and to what heat does to matter, and it's the same physics you already know from your own kitchen without ever thinking of it as physics. When you heat something, it expands. When you cool it, it contracts. A jar lid that won't budge loosens under hot water because the metal swells a little in the warmth. Warm air rises and fills more space, cold air sinks and draws in. Heat pushes matter apart, ever so slightly. Cold lets it settle back together, tighter. This is true of a lid, true of the air in a room, and true, on a scale almost too large to feel, of the inside of a planet. Mercury, when it was born, was hot. Blazingly, molten hot, a ball of fire and liquid metal fresh from the violence of the solar system's building. And ever since that beginning, for billions of years, it has been doing the one thing a hot object surrounded by cold, empty space cannot help but do. It has been losing its heat, radiating it away into the dark, a little every year, cooling from the outside in, the way a fired iron cools on the forge, the way a stone pulled from a bonfire slowly gives its warmth back to the night air until you can hold it in your bare hand. Space is very, very cold and very, very empty, and a warm planet adrift in it has nowhere to keep its heat forever. So it bleeds it away, and as the inside cools, the inside contracts. It settles. It draws inward, tighter and smaller, atom by atom, and the crust on top, riding on a shrinking interior, is left with too much surface for the world beneath it. And it wrinkles, and it cracks, and it lifts into cliffs. But here is where Mercury's version of this ordinary story turns extraordinary, and where I want to plant the first real seed of the strangeness that will keep unfolding all night. Most of what is cooling and shrinking inside Mercury is not rock. It's iron. Metal, because Mercury, alone among the planets, is built around a core of iron so enormous that it hardly seems possible, a heart of metal that takes up most of the whole world, leaving only a thin skin of stone around it. We'll spend real time down in that core later, because it is one of the great puzzles of the solar system, a core so oversized that scientists still argue about how it got that way. But for tonight, for this first slow descent, all you need to hold is this. The thing shrinking at Mercury's center is a vast ball of iron, slowly freezing. And when iron cools, when a molten metal turns solid, it doesn't just cool, it packs itself down. The atoms in liquid metal drift loosely, taking up room. As the metal freezes into solid, those atoms lock into a tight, ordered arrangement and pull closer together, and the whole mass takes up less space than it did as a liquid. The metal contracts as it solidifies. And so Mercury's freezing iron heart is pulling the whole planet inward from the inside, and the crust above has no choice but to follow, breaking and crumpling to keep up. That is the spine of the entire story I want to walk you along tonight, so let me say it plainly, gently, once, so you can carry it into whatever comes next. Mercury is a planet slowly crushing itself as its iron core freezes. Everything else, every impossible detail we'll get to, the cliffs, the giant core, the ice that shouldn't exist, and yes, even the diamond, all of it hangs off that one thermodynamic thread. A hot metal world, born in fire, cooling for 4.5 billion years, contracting as it cools, wrinkling its stone skin into cliffs as it shrinks, and possibly, quietly, leaving evidence of that whole process buried deep in its interior in a form you would never in 100 years guess. The planet is dying by shrinking, and the diamond, if it's really there, may be the receipt. I said that word, and I'll let it sit there in the dark for now, unopened, the way you'd set a wrapped thing on the table and agree to open it later. Diamond, there is a study from 2024 that proposes something almost impossible to believe about the deep inside of this small burned planet, and when we get there I'm going to walk you through it slowly and honestly. Because the truth of it is far more beautiful than the breathless version you might have half heard. But not yet. Let the loop stay open. Let it pull at you gently as we go. Just know that the reason a serious scientist could even begin to imagine diamond forming inside Mercury is tangled up with everything we've just talked about. The heat, the cooling, the pressure of a planet packing in on itself, the strange carbon-rich chemistry of a world that started as a ball of fire. The shrinking and the diamond are not two separate wonders. They are two ends of the same thread. But stay up here on the surface with me a moment longer, among the cliffs, because I don't want to rush past how eerie this landscape really is once you understand what you're looking at. Picture yourself set down on Mercury's grey plains. There's no air, so there's no sound and no sky blue, just black overhead even in full day, and the ground stretching away in soft rolling grey, cratered, ancient, older than almost any surface in the solar system. Some of this crust has sat here largely unchanged for billions of years, so heavily pocked with old impacts that there's barely room for a new one. It is, in that sense, one of the oldest faces in the solar system, a landscape that remembers the early bombardment when the planets were young and the sky rained rock. And yet, cutting across all that ancientness are these cliffs, these long lobate scarps snaking over the old craters, sometimes running right through them, slicing a crater wall in half and lifting one side of the crater floor above the other, which tells you the cliff came after the crater, that the shrinking was still shaping the land long after the great bombardment ended. An ancient surface and a living interior working against each other. A face that looks dead and a heart that will not stop moving. That contradiction, an old skin over a restless core, is the first of Mercury's paradoxes, and once you notice it, you start to see the same shape everywhere. Something that should be finished, that isn't. Something that should be impossible, that is nonetheless simply, quietly true. And these cliffs are not gentle slopes. When we say a scarp can rise 2 or 3 kilometers, let me put that against something you can feel in your body. 2 to 3 kilometers of vertical rise is taller than most mountains you've ever stood beneath. It's a wall of stone that would take the tallest things humans have ever built and stack them and still not reach the top. And unlike a mountain, which rises to a peak and comes back down the other side, a thrust fault scarp is more like a single enormous step. A place where the whole landscape is simply at one height on this side and a couple of kilometers lower on that side, with a long curving cliff face between them, running for hundreds of kilometers into the grey distance. A step in a planet. A place where the crust squeezed past what it could bear, finally broke and rode up over itself, and froze there, mid-shove, a wave of stone that will never come down. And the thing I keep coming back to, the thing I want you to drift off holding, is that at least some of these steps in the planet may not be finished rising. The freshest, smallest scarps, the crisp ones, the ones that haven't been softened by the slow rain of tiny impacts, they hint that the crust is still breaking, still lifting, in our own era. Not in some vanished ancient chapter, but now. Which means that somewhere out there, tonight, on that small world close to the sun, invisible to every eye, a piece of ground may have shifted since you lay down. A cliff may be a hair taller than it was this morning. The planet is a fraction smaller than it was 1,000 years ago, and will be smaller still 1,000 years from now, and it is doing this the only way it knows how. Silently, patiently, by cracking its own stone skin and shrugging the pieces up into cliffs, because its iron heart is cooling, and cooling metal contracts, and there is nothing anywhere in the universe that can stop a warm thing surrounded by cold from slowly giving up its heat. Let me linger on that, because it's the kind of fact that is easier to feel than to think, and feeling is what you want as you settle towards sleep. The whole of Mercury's shrinking, all of it, every cliff, is powered by nothing more dramatic than heat leaving. The most ordinary thing in the world. The reason your tea goes cold on the nightstand, the reason a house cools after the fire dies down, the reason a hand-warmed stone eventually goes cool again in your palm. That same humble physics, scaled up to the size of a planet and stretched across billions of years, has taken a whole world and pulled it inward and folded its surface into cliffs you could see from space. There is something enormously restful in that to me, that the grandest, strangest features of an alien world come from the gentlest, most familiar process. Warmth, leaving, slowly, the way warmth is leaving the day right now, the way the room is settling into that cooler stillness of night, the way your own thoughts are, I hope, drawing inward, softening, letting go of their sharp edges, the same way a young scarp will one day be softened by the ages. The people who first mapped these cliffs in real detail did it with a spacecraft. And the numbers I've been giving you, the 5 to 7 kilometers of lost radius, the count of all these thousands of contractional features wrapped around the planet, came in large part from a careful global mapping study in 2014, led by a scientist named Byrne and his colleagues, who took the images of Mercury's whole surface and added up every wrinkle cliff, every ridge, every thrust fault, and worked backward from the total amount of crumpling to how much the planet as a whole must have shrunk to produce it all. Because that's how you weigh the shrinking of a world you cannot squeeze in your hands. You count its wrinkles. You measure how much crust has been shoved up and folded over, everywhere, all around the globe, and you ask, how much smaller would the planet have to become for all of this crowding to make sense? And the answer that came back was larger than anyone had expected in the earliest days of exploring Mercury, when the first quick glimpses from long ago suggested only a kilometer or two. The better we looked, the more shrinking we found. Several kilometers of radius, gone, a whole planet, measurably smaller than it was born. And every one of those wrinkles was made by the same slow crush, the same freezing heart, the same physics of cooling metal that has been running without pause since the planet formed. So when you look at a map of Mercury covered in these curving cliff lines, you are not looking at scenery. You are looking at a record, a ledger. Every scarp is an entry in the account of how much this planet has cooled and how much it has therefore shrunk, written into stone, kilometers high, hundreds of kilometers long, and readable across the whole grey face of the world. The cliffs are the receipt for the heat that has left. And I keep using that word, receipt, on purpose, because I want you to hold it loosely as we drift toward the deeper strangeness still to come. The monstrous iron core we've only just glanced at, the ice that clings to a planet next to a furnace, and the thing crystallized in the dark at the boundary between the core and the rock above it. The cliffs are the receipt written on the outside, where anyone with a spacecraft can read it. But the same story of a cooling, contracting, iron-hearted world may have left another kind of receipt far down inside, in a form so unexpected that when a research team proposed it in 2024, it made headlines all over a world that mostly imagines Mercury, if it imagines Mercury at all, as a dull grey rock not worth a second thought. They are so wrong about that, and I'd love to spend the rest of tonight showing you exactly how wrong, layer by layer, going down. Because so far we've only stayed near the surface, walking among the cliffs, learning the one central thing, that this planet is shrinking, that it wrinkles its crust into kilometre-high scarps as it does, that some of those scarps may still be rising in our own time, and that all of it traces back to a heart of iron slowly freezing at the centre of a world. That's the foundation. That's the spine. Everything else we'll lay along it. So let's go down further, past the broken crust, toward that impossible core, the one that takes up most of the planet, the one that by every reasonable expectation should have frozen solid billions of years ago, and yet somehow, against all the odds a small world should face, is still partly liquid, still moving, still generating a faint magnetic field out there in the dark. Because before we can understand the diamond, before we can even properly understand the ice, we have to understand the heart. And the heart of Mercury is where the paradoxes really begin. Think, for a moment, about what a core is supposed to do. In a rocky planet, the core is the iron heart, the densest, heaviest part. The stuff that sank first during the chaotic early heat of the solar system, when everything was still molten and gravity was sorting materials by weight, pulling the heavy iron down through the liquid rock like stones settling through slow water. Every rocky planet has one. Earth has one. Mars has one. Venus almost certainly has one, though we have never been able to look directly at it. And Mercury has one too. The difference is that Mercury's is something else entirely, something that does not fit neatly into the story we thought we understood about how planets form and cool and age, and when you encounter it for the first time as a number on a page, the number does not quite register. You read it, and then you read it again, and you think that somebody must have made a mistake, because the number is simply too large. The core of Mercury occupies roughly 85% of the planet's radius, not 85% of the volume, though the volume fraction is staggering enough in its own right. Somewhere in the range of 55 to 70% of the total volume of the planet is iron core, compared to perhaps 15% for Earth. The radius figure is the one that lands hardest, because it gives you the most direct sense of what you are dealing with at the level of a cross-section, a simple picture of a circle within a circle. If you were to slice Mercury cleanly in half and stand looking at the cut face, the outer shell of rock and crust that you associate with a planet's surface, the part where the cliffs we have been talking about are raised and the craters are pressed in, and the strange bright hollows open in the ground, that entire outer shell would be a relatively thin rind wrapped around an iron ball that takes up almost all of the space. It is something like the difference between the skin of an apple and the apple itself, except that even that comparison is too generous to the skin. Mercury is at its core, and the phrase is almost more literal here than it is figurative, predominantly an iron world. The rock is a coating on a metal planet. Earth's uncompressed density, that is, the density you would measure if you could somehow relieve all of the internal gravitational pressure that compression produces and let the material expand back to its natural state, is lower than Mercury's. Of all the major bodies in the solar system that we know well enough to calculate, Mercury has the highest uncompressed density of any. Its measured density overall is about 43 grams per cubic centimetre, which is close to Earth's, and if you only knew those numbers side by side, you might think they were similar kinds of worlds. But Earth is much larger, and a larger planet produces much greater internal pressures, which squeeze its material to higher densities automatically, when you correct for that compression. When you ask what Mercury's material would actually weigh under neutral conditions, Mercury comes out heavier, more iron per unit of actual composition than any other planet we know. And the cliffs on the outside, the shrinking crust, the whole story of contraction is the consequence of that iron dominance playing out across geological time. You cannot separate the cliffs from the core. The receipt is written on the surface, yes, but the ledger is kept inside. And here is where the first impossibility arrives. A body the size of Mercury should have finished cooling and solidifying billions of years ago. This is not a controversial claim, and it is not something we arrived at by accident. It follows from basic principles of heat loss, the same principles that govern why a small object cools faster in a room than a large one, why a marble left on a warm windowsill cools to room temperature long before a heavy iron pot. The ratio of surface area to volume determines how quickly heat can escape, and a small planet has a large surface area relative to its interior, which means heat bleeds away faster. Mars is larger than Mercury and is thought to have had a more dynamic geological past, but Mars today appears to have a mostly or entirely solidified core and no global magnetic field generated by an active dynamo. Mars is geologically quiet in that sense, or very nearly so. Mercury is smaller than Mars. Mercury should, by the same logic applied more forcefully, have been a cold, frozen, inert iron ball for most of its history. The heat generated during its formation, the tremendous energy released by impacts and gravitational compression and radioactive decay in the early solar system, should have leaked away into space long ago, leaving everything inside frozen solid. What Mariner 10 found in 1974 and 1975, when it became the only spacecraft to visit Mercury for the next 35 years, was not a cold, frozen world in that magnetic sense. It detected something that should not have been there. A global magnetic field, faint but unambiguous, wrapping the planet in a kind of invisible cocoon, the way Earth's much stronger field wraps this world. Magnetic fields of this planetary kind, the ones that surround an entire world rather than being locked into rocks from an ancient era, are generated by a process called a dynamo, the circulation of electrically conducting fluid in the interior, driven by heat and rotation, creating electrical currents that in turn produce magnetic fields, which influence the fluid, which influences the currents. In a coupled system that can sustain itself for as long as the fluid keeps moving. Earth's dynamo runs on the convection of its liquid outer iron core around its solid inner core. The key word, the word that makes it work, is liquid. The fluid has to be moving. Mercury's magnetic field, detected by Mariner 10 and then studied in close and careful detail when Messenger entered orbit in March of 2011 and spent 4 years mapping the planet, is weak, very weak. It registers at something close to 1% of Earth's field strength, which is not nothing, but it is the quietest sustained global magnetic field we know of among the planets. Yet it is there. The field is real. It is generated by an active dynamo. And an active dynamo means a liquid outer core that is still circulating, still churning slowly in the dark, still warm enough to remain in motion rather than having frozen into a solid iron block. A body this small, this close to the total exhaustion of its internal heat, has no right to this field by the simple arithmetic of planetary cooling, and yet the arithmetic is wrong, or rather the full story is more complicated than the simple version, and the full story is where the interesting science lives. There are things that can slow the cooling of a core and keep it from solidifying. Certain chemical additions to an iron melt lower its freezing point. The way salt on an icy road lowers the temperature at which ice forms. Sulfur is one such addition, and the deep interior of Mercury is believed, based on the evidence Messenger gathered from the surface chemistry and from models of the interior, to contain significant amounts of sulfur in the iron melt. The presence of sulfur in Mercury's core would lower the solidification temperature, meaning the core would need to lose more heat before it begins to freeze, buying it additional time. Silicon may also be present in the mix. The details of precisely which light elements are dissolved into Mercury's iron core remain an active area of research and have not been settled, but the broad point is that the chemistry of the deep interior is not pure iron, and the chemical impurities that are present likely play a role in maintaining the liquid state for longer than simple iron would allow. There is also the question of how the solidification proceeds. In Earth's interior, there is a solid inner core growing at the center, surrounded by the liquid outer core where the dynamo operates. The inner core grows slowly as heat escapes, and the iron at the very center reaches its solidification point. Mercury likely has a similar arrangement. A solid inner core at the center with a liquid layer above it, and the properties of the boundary between the solid and liquid regions affect the vigor and character of the convection that drives the dynamo. Messenger's measurements of Mercury's gravitational field and the way the planet responds dynamically to gravitational tugs from the Sun and from Jupiter over long time periods. A kind of precise wobbling that carries information about what the interior is made of and how it is structured, confirmed that the core is at least partially liquid. The planet would not wobble the way it does, the outer shell responding slightly differently from a perfectly rigid body, if everything inside were solid all the way through. The liquid is there. The dynamo is real. And then there is this. The magnetic field Mercury has is unusual not only for its weakness, but for its shape. On Earth, the magnetic poles are reasonably close to the geographic poles. Not perfectly aligned, and they wander over time, but the magnetic field, taken broadly, is roughly centered on the planet's axis of rotation. Mercury's is not. The magnetic equator, the line around the planet where the magnetic field runs perfectly horizontal, the dividing boundary between the northern and southern magnetic hemispheres, is offset from the geographic equator by about 20% of Mercury's radius toward the north. The field is not centered on the planet. It is, in a sense, lopsided, its axis shifted so that the northern magnetic hemisphere is larger than the southern, the whole invisible structure displaced toward the north pole of the planet as if someone reached inside and nudged it. A lopsided dynamo running in a liquid iron core that by all expectations should have solidified long before we arrived to measure it. Messenger's magnetometer measured this offset with considerable precision. It is one of the more striking discoveries that mission produced, because it suggests that the convection inside the core is not symmetric, that something about the way heat escapes from the interior drives fluid motion that concentrates the magnetic field generation in one hemisphere more than the other. What that something is, exactly, is not yet known. It may have to do with the structure of the boundary between the liquid core and the rocky mantle above it. The core-mantle boundary, which is a surface of enormous importance for what happens inside the planet, and to which we will return, because it is also where the most unexpected of all the proposals about Mercury's interior is situated. But for now, the asymmetry of the field stands as one more piece of evidence that the deep interior of this small world is more complex, more active, and more surprising than it had any right to be. So the first impossibility, the live dynamo in a body too small to sustain one, is accepted by the science as real. The evidence from Mariner 10, built upon by Messenger's 4 years of orbital study, is clear enough on that point. What remains genuinely open, where the science has not converged on a single answer that everyone agrees with, is the deeper question behind the impossibility. Not whether the core is strange, but why. Why is the core so large relative to the planet? There are three main families of explanation, and they are not entirely mutually exclusive, meaning pieces of more than one could be true simultaneously. None of them has been definitively confirmed, and each carries different implications for what the planet looked like in its earliest history, and for how we should understand the formation of rocky planets generally. This is, in other words, not a settled question that I am explaining to you, but a genuinely active scientific puzzle that researchers are still working on. The first family of explanations centers on a catastrophic collision. Early in the solar system's history, the first 100 million years or so after the Sun formed, the inner solar system was a violent place, filled with planetesimals and protoplanets of varying sizes jostling and intersecting, and sometimes colliding at enormous speeds. Earth itself is thought to have been struck by a Mars-sized body in an impact that stripped away material and ultimately led to the formation of the Moon. The hypothesis for Mercury is something analogous, that early Mercury was once a larger body, one with a more normal proportion of rocky mantle to iron core, and that at some point in the solar system's chaotic early history it was struck by another large body, a collision that stripped away a substantial fraction of Mercury's outer rocky layers. The iron core, being the densest part and concentrated at the center, survived the impact more or less intact, while much of the lighter rock and silicate material was ejected into space, some of it perhaps absorbed by the Sun, some scattered into the broader solar system, some remaining in orbit around Mercury briefly before dispersing. What was left behind was a body far more enriched in iron relative to total mass than it had been before. A planetary remnant with a core that had not changed enormously but now sat inside a much diminished rocky envelope. A stripped world. The second family involves the Sun itself and the conditions that prevailed in the innermost regions of the young solar system. In the early period, the nascent Sun was more luminous and more energetic than it is today in certain respects, and the inner edge of the solar system where Mercury formed was an intensely irradiated environment. One version of this hypothesis proposes that the extreme temperatures close to the Sun in the early disk of gas and dust from which the planets coalesced, the protoplanetary disk, were high enough to vaporize or drive off silicate materials that would otherwise have contributed to Mercury's rocky mantle, leaving behind only the more refractory, heat-resistant components, which happened to be heavier and more iron-rich. Another version focuses on the early solar wind, which was also much more powerful than the one Mercury experiences today, and which may have selectively eroded lighter, less gravitationally bound material from Mercury's outer layers over an extended period of time. In either version, the Sun itself is the sculptor, carving Mercury down to its iron-dominated state, not through a single catastrophic blow, but through a sustained environmental process. The third family is perhaps the simplest in concept, though it leads to some complicated implications for planetary formation theory. It holds that Mercury formed where it is, in conditions that were simply iron-rich to begin with, that the composition of the materials from which it accreted in the innermost part of the solar disk favored iron over silicates, and that the disproportionate core is therefore a compositional inheritance rather than the result of something violent or stripping happening afterward. Mercury, on this view, is simply what you get when a rocky planet forms very close to a young star where iron-rich solids condense, preferentially. The strangeness is baked in from the start, not added or subtracted later. These three possibilities lead to different predictions about what Messenger should have found and what Bepi Colombo should find. about the detailed chemistry of the surface and the structure of the boundary between the mantle and the core, about whether there are subtle signatures in the rocks that record an ancient catastrophic event. Messenger gave us an enormous amount of new information about the surface chemistry, and much of it has been used to evaluate these hypotheses, with no single answer emerging as a clear winner. Parts of the data favor the giant impact scenario in some ways and complicate it in others. Parts of the surface chemistry seem easier to explain if Mercury formed in an iron-rich environment without requiring a later stripping event. The honest position, the one that matches the state of the science, is that all three mechanisms may have contributed to varying degrees, and that disentangling them will require the more precise measurements of the interior structure, the core size, the mantle thickness, and the boundary conditions at depth that Bepi-Colombo is designed to provide. The question of why Mercury is what it is remains open, and it is one of the genuinely important open questions in planetary science, because whatever happened to Mercury may tell us something broader about the violence and the sorting mechanisms of the early solar system, and about how common or rare such iron-dominated worlds might be elsewhere in the galaxy. Around other stars, where we are increasingly able to detect the small, close-in rocky planets that might be Mercury's analogues. There is one more thing about Mercury's relationship to the Sun that is worth settling into before we go further inward, because it speaks to the particular strangeness of a world that has had its entire life shaped by proximity to such overwhelming gravity and radiation. Mercury does not orbit the Sun in quite the way you might expect. It does not rotate once per orbit, tidally locked the way the Moon is locked to Earth, always showing one face and hiding the other, always with one hemisphere in permanent sunlight and one in permanent darkness. It does not rotate many times per orbit the way Earth does, producing a relatively regular sequence of days and nights. Instead, Mercury occupies a peculiar middle ground, a resonance that took scientists some time to work out and that turned out to be more interesting than either of the simpler options. Mercury rotates exactly 3 times on its axis for every 2 orbits it completes around the Sun, a 3-to-2 resonance, locked into that precise ratio by the Sun's gravity acting on Mercury's slightly elongated shape across millions of years, gently nudging the rotation until it settled into a configuration where the gravitational torques balanced and the planet could continue stably. The consequence of this resonance, when you work through the geometry carefully, is that a single solar day on Mercury, measured not from star to star, but from noon to noon, from the moment the Sun reaches its highest point in the sky to the next such moment, lasts about 176 Earth days. Longer than Mercury's own year, which is 88 Earth days, the time it takes to complete one orbit. Mercury manages to travel twice around the Sun in the time it takes the Sun to cross the sky once as seen from Mercury's surface. If you were standing on Mercury and watching the Sun, patient enough to track it across weeks and months, you would see it do something that appears nowhere else among the major planets: move, slow and enormous, across the sky, pause, reverse briefly, then continue. A consequence of the combination of the orbital motion and the rotation in a resonance that produces a sky unlike any other in the solar system. It was Giuseppe Colombo, an Italian mathematician and aerospace engineer working in the 1960s, who first understood this resonance correctly. Before Colombo, the best observations from Earth had suggested that Mercury might be tidally locked in a 1-to-1 resonance, always keeping the same face toward the Sun, a natural enough assumption given how close it orbits. Mariner 10 was still many years away, and the data from Earth were difficult to interpret with confidence. Colombo looked at the numbers and argued that a 3:2 resonance was actually more dynamically natural, a more stable configuration given the orbital eccentricity Mercury has, the most eccentric orbit of any planet at about 0.21, which means the distance between Mercury and the Sun varies considerably as it orbits, approaching much closer at some points than at others. The gravitational tugs are stronger when the planet is closer, and an eccentric orbit with a 3:2 resonance can be a particularly stable arrangement because the alignment between the planet's elongated axis and the direction to the Sun repeats in a regular pattern that minimizes the net torque over time. Colombo worked this out before Mariner 10 arrived to confirm it. When the spacecraft did arrive, in 1974, it found exactly what Colombo had predicted. The resonance was real, the rotation rate matched the theory, and an Italian mathematician who had never sent a spacecraft anywhere had nonetheless, through the patient application of orbital mechanics, seen more clearly into the truth of Mercury's motion than anyone else of his era. The mission that is now on its way to Mercury, the one that carries the most sophisticated suite of instruments ever aimed at that world, bears his name. Bepi Colombo, the joint European and Japanese mission launched in October of 2018, is named for Giuseppe Colombo, who died in 1984 without seeing a spacecraft in orbit around the planet he understood so well. The name feels appropriate in a way that goes beyond simple tribute. Colombo's insight was that Mercury's strangeness was not a puzzle to be dismissed or explained away as a one-to-one locked body too simple to be interesting, but a genuinely novel configuration worth understanding precisely. A resonance that only made sense when you took seriously how Mercury's orbit, its shape, and the Sun's gravity had conspired together over vast time to produce something unusual. That approach, of taking Mercury's strangeness seriously, of not assuming it must be simpler or more boring than it appears, is the same approach that the science of the last 2 decades has applied to everything else about the planet. And it keeps yielding the same result. There is more here than first appears, and the strangeness runs all the way down. The temperature swings that the 176-day solar day produces are staggering. Because there is no real atmosphere to speak of, no significant blanket of gas to redistribute heat and moderate temperatures the way Earth's atmosphere does, even on a calm night. The surface responds almost directly to whatever the sun delivers. At local noon in direct sunlight, the surface reaches temperatures of around 430 degrees Celsius, well above the point where lead melts, hot enough that ordinary rock glows faintly if you could see into the infrared. And then the long night comes, and in the absence of that atmospheric blanket, the heat radiates away into space with nothing to hold it back, and temperatures drop to around negative 180 degrees Celsius. A swing of more than 600 degrees between the hottest and coldest conditions, experienced not in a sharp day-night cycle, but across a day that lasts 6 Earth months and a night of equal length. The same surface that was hot enough to melt lead will, 6 months later, be cold enough to freeze carbon dioxide solid. And yet Mercury has what amounts to a thin, vanishing ghost of an atmosphere, not a true atmosphere in any meaningful sense, but a so-called exosphere, a collection of atoms clinging loosely around the planet, so sparse that individual atoms rarely if ever collide with one another, more like a region where stray particles exist than a gas in the usual sense. Sodium, Oxygen, hydrogen, helium, potassium, atoms kicked off the surface by the solar wind and by the steady rain of micrometeorites arriving from space, released into the near vacuum above the surface, and then eventually lost again to space. Sodium in particular has been detected in this exosphere and found to form a faint, elongated structure streaming away from Mercury on the side away from the Sun, a kind of ghostly comet tail made of sodium atoms pushed by the pressure of sunlight extending far into space behind the planet. Mercury, the innermost planet, the dense iron world wrapped in a thin skin of rock, has a comet tail made of sodium. The details of this world keep arriving like that, each one quietly remarkable, each one the consequence of some extreme or unusual condition that turns out to produce an effect you would not have predicted without thinking carefully about the physics. But none of these details, not the resonance, not the exosphere, not the temperature swings, not the slightly too large surface gravity at about 38% of Earth's, despite the planet being so much smaller than Mars, none of them is quite as significant as the paradox of the core itself. The core is the heart of the matter, and the heart is strange, and the strangeness deepens when you begin to consider what might be happening not at the center of the core, where the solid iron inner regions likely sit, but at the boundary between the iron core and the rocky mantle above it, a surface deep inside the planet where the conditions are unlike anything we can directly observe and can only study through experiments conducted in laboratories here on Earth, pressing materials to extraordinary pressures in devices built to recreate the conditions at the center of worlds and through the mathematical machinery of high-pressure geophysics. Because there is a third receipt, not written in cliffs on the surface, not written in the weakness and offset of the magnetic field, but potentially written in the material itself at that core-mantle boundary, in a form that a team of researchers proposed in 2024, and that requires, before it can be understood, a proper account of what Mercury's surface is made of and what that surface chemistry tells us about what happened deep inside the planet billions of years ago when it was young and hot and everything was still in motion. The surface of Mercury is dark, darker than you might expect. When MESSENGER began returning images and spectral data from orbit, one of the things that became clear is that the surface is not the pale grey of the Moon, the pale grey you might assume a cratered rocky body close to the Sun would have. Mercury is darker, and the reason it is darker, the material responsible for absorbing more of the light that falls on it, turns out to be carbon. Graphite, specifically the same material that forms the core of a pencil, the same material that can, under the right conditions of pressure and temperature, be transformed into something else entirely, something much harder, something that has captured the human imagination in a way that graphite never quite has. MESSENGER's instruments found that Mercury's surface is anomalously enriched in carbon. And the explanation for that enrichment, the one that fits best with the other things MESSENGER found about the planet's geology and history, is that Mercury once had a magma ocean, a global layer of molten rock covering the young planet's entire surface in its earliest history, and that this magma ocean was unusually rich in carbon. As that magma ocean slowly cooled and solidified over millions of years, the carbon crystallized out, and because graphite is less dense than the surrounding silicate minerals in a Mercury composition melt, it floated upward rather than sinking, accumulating at the surface in a dark carbon-rich layer. That layer was then buried under subsequent volcanic eruptions and impact ejecta over billions of years of subsequent history, but it left traces, detectable by Messenger's instruments as an unusually high carbon content in the surface rocks, a ghost of that ancient magma ocean preserved in the chemistry of the crust. The surface graphite is the observational anchor. It is a real measurement, a confirmed feature of Mercury's surface that Messenger established beyond reasonable doubt. And it matters here because it tells us something about the carbon content of Mercury's interior more broadly, about the kind of planet this is at the level of its raw materials, and about the conditions that might prevail deep inside at the core-mantle boundary, where the pressures are extreme and the temperatures have been evolving over the planet's entire history. It was that connection, from the observed surface graphite to the proposed conditions at depth, that a team of researchers followed when they designed the experiments that led to the proposal published in Nature Communications in 2024. The team at the center of that 2024 proposal was led by Yanhao Lin, working at the Center for High-Pressure Science and Technology Advanced Research. And what they set out to do was not speculative in the loose sense that word sometimes carries in popular accounts of planetary science. They were not imagining what Mercury might be like. They were attempting to recreate it in the most literal sense available to laboratory physics by subjecting materials of the right composition to the pressures and temperatures that would prevail at the boundary between Mercury's iron core and the rocky mantle above it, and then observing what those materials did. The instrument they used for this is called a multi-anvil high-pressure apparatus. It is, in its essence, a machine for making the interior of a planet in a space you could hold in your hands. The principle is straightforward, even if the engineering is not. A sample of material, carefully composed to match what geochemists believe Mercury's deep interior looks like in terms of its chemical makeup, is placed inside a small assembly of ceramic and metal components. And then a set of tungsten carbide anvils, massive and precisely machined, are driven toward one another by hydraulic rams, squeezing the sample from multiple directions simultaneously until the pressures inside that tiny capsule match what would exist hundreds of kilometers beneath Mercury's surface. At the same time, the sample is heated electrically to the temperatures that prevail at those depths. For a few minutes or a few hours, that small capsule is, as closely as the physics allows, a piece of Mercury's deep interior. And what Lin and the team found when they opened those capsules and examined what had crystallized was consistent with a prediction that had actually been made before, though with less precision and with less attention to one particular variable that turned out to matter enormously. The prediction, in its basic form, was this: Mercury's interior contains carbon. We know this because the surface tells us so. The graphite there, that dark anomalous carbon content that Messenger measured directly, pointing back to a planet that formed from carbon-rich material and that once had a carbon-rich magma ocean. Some of that carbon was driven deep into the interior as the planet formed and differentiated. As the iron sank and the rock rose and the young planet sorted itself out by density over the first tens of millions of years of its history. Carbon that ended up in the deep interior, at the boundary between the iron core and the silicate mantle, would have been subjected to pressures and temperatures that, on Earth, are the conditions under which diamond forms. The idea that Mercury might have diamond at depth was not, therefore, a wild flight of imagination. It followed from basic mineralogy and planetary physics. But the question of how much, and in what form, and how thick any such layer might be, required the kind of experimental constraints that only a high-pressure apparatus can provide. What the earlier estimates had not fully accounted for was sulfur. Mercury's iron core is not pure iron. It contains lighter elements mixed in, and sulfur is one of them, present in significant proportions. And when the researchers incorporated sulfur into their experimental samples, something shifted in the results. The presence of sulfur changes the conditions under which carbon crystallizes from the iron melt, changes the solubility of carbon in the liquid core material, and pushes the predictions in a direction that allows for a thicker, more substantial diamond layer than earlier models had suggested. When they ran the experiments with sulfur properly accounted for, the numbers that came out pointed toward a layer of diamond at the core-mantle boundary that might be, in the scenario their models describe, up to approximately 15 kilometers thick. 15 kilometers. 12 miles, give or take. A shell of crystallized carbon sitting at the boundary between the iron ocean below and the rocky mantle above, formed not in an instant, but over the billions of years of Mercury's cooling history, as the planet slowly lost the heat it was born with, as the deep interior gradually descended through the temperatures and pressures at which carbon, dissolved in the liquid iron, preferred to precipitate out as something solid. It is worth pausing here, because the number is so striking that it invites a very particular kind of misreading, the kind that spread rapidly when this study was published and that generated a wave of headlines that were, in the most polite framing, somewhat misleading. The headlines said, in various forms, that Mercury might be full of diamonds, or that there was a diamond planet waiting to be exploited, or that future missions might one day harvest the riches buried inside the innermost world. And this is worth addressing directly, because the misreading is not merely inaccurate in the way that science communication sometimes oversimplifies. It misunderstands the nature of the claim so completely that it inverts what makes the claim interesting. The proposed diamond layer, if it exists, sits at the core-mantle boundary. That boundary is not a place on the surface. It is not even a place that any instrument can reach directly. It is buried under the entirety of Mercury's rocky mantle, which is itself already compressed under the weight of everything above it, and then under the crushing pressure of the core below. And the whole assembly sits at depths and under pressures that no human technology could penetrate, even in principle, with anything currently conceivable. The core-mantle boundary on Mercury is somewhere in the neighborhood of several hundred kilometers beneath the surface, in a realm where pressures run to millions of atmospheres and temperatures hold at thousands of degrees. The diamond there, if it is there, is not sitting in a vault waiting for retrieval. It is a structural feature of a planetary interior as inaccessible as the center of the Earth, and considerably less accessible than that in practical terms, because Mercury is a world we have only ever orbited with a single spacecraft. To call it a resource is to confuse a geological description with a mining prospect, and the confusion does a disservice to the actual science, which is far more interesting than any fantasy of extraction. What the proposed layer represents, if the experiments and models are correct, is not treasure in any ordinary sense. It is information. It is a record. A layer of diamond crystallizing at the core-mantle boundary over billions of years would carry within its structure the imprint of the conditions under which it formed, the temperature gradients, the chemical compositions, the pressures. And beyond that, the researchers noted something that pulls the diamond hypothesis into direct contact with one of the other great puzzles of Mercury's interior, the puzzle of the magnetic field. Mercury's magnetic field, as the previous part of this story established, is weak but real, generated by a dynamo operating in the liquid outer core, and it is offset, its equator displaced northward from the planet's geographic center by roughly 20% of Mercury's radius. Both of those features, the weakness and the offset, remain incompletely explained, and models of the dynamo are still working toward a picture that can account for both of them simultaneously. What Lin and colleagues proposed is that a layer of diamond at the core-mantle boundary might actually influence the dynamo in measurable ways. Diamond is an extraordinarily good conductor of heat, among the best of any natural material. And a diamond layer sitting at the boundary between the core and the mantle could alter the pattern of heat flow out of the core, creating asymmetries or gradients in the way that heat moves, which in turn would shape the convective motions in the liquid outer core, which are what drive the dynamo in the first place. The magnetic field that Messenger measured then might bear the fingerprints of a diamond layer that no instrument has ever directly seen. This proposed connection between the diamond and the dynamo is, to be clear, a hypothesis built on other hypotheses. It is a chain of reasoning that depends on the diamond layer being real, on the diamond layer being thick enough to matter thermally, and on the details of how heat flow through the core-mantle boundary influences Mercury's particular dynamo. None of these links in the chain have been independently confirmed. But the chain is not arbitrary. Each link follows from established physics and from the experimental results that Lin's team published. And the fact that the proposed layer might be detectable indirectly through its influence on a magnetic field that has already been measured, gives Bepi-Colombo's magnetometers a reason to care about it, a reason to look for patterns in the field that might be explained by a crystallized carbon shell that nobody can otherwise see. This is how planetary science often works, not with a single dramatic confirmation, but with an accumulation of indirect evidence, each measurement constraining the possibilities slightly further, until the space of plausible models narrows to something that can be described with confidence. The surface graphite that Messenger measured is one constraint. The magnetic field that Mariner 10 first detected in 1974 and 1975, and that Messenger characterized in detail over 4 years of orbital observation, is another. The high-pressure experiments that Lin's team published in 2024 are a third, showing that the physics of carbon crystallization under Mercury interior conditions is consistent with a layer of the thickness they propose. Bepi-Colombo's measurements, when the spacecraft finally settles into orbit in late 2026, will add another layer of constraints still, tighter and more precise than anything that has come before. But before arriving at Bepi-Colombo, there is another piece of Mercury's story that belongs here, because it is connected to the carbon, connected to the darkness, connected to the idea of a world that hoards things in unexpected places, and because it is, in its own right, one of the most counterintuitive facts in all of planetary science. There is water ice on Mercury. Not a little, not a trace, not an ambiguous chemical signature that might be ice or might be something else. There is water ice, confirmed, sitting in the craters at Mercury's poles. Hundreds of billions of tons of it by the most conservative estimates, and possibly as much as 1 trillion tons by the more generous ones, locked in place and preserved by conditions that seem, on first hearing, almost absurd, given that the planet in question is the closest world to the Sun. The story of how this discovery came about has 2 chapters, and the first was not written by any spacecraft. It was written by a radio telescope on the surface of the Earth. In the early 1990s, astronomers using the Arecibo Observatory in Puerto Rico were bouncing radar signals off Mercury and analyzing the echoes that came back. And what they found at the planet's poles was anomalous. The radar return from the polar regions was unusually bright, and bright radar returns from planetary surfaces are often associated with one particular thing: water ice. The same signature had been seen at Mars's poles, where ice is known to exist. Seeing it at Mercury was startling enough that it prompted debate for nearly 2 decades. The idea that the closest planet to the Sun might have ice seemed almost paradoxical, and skeptics proposed alternative explanations: sulfur compounds, unusual rock types, other materials that could produce a similar radar signature. The question remained open, a puzzle with no definitive answer, until Messenger arrived and settled it. Messenger carried an instrument called a neutron spectrometer, and neutron spectrometers are sensitive to hydrogen in ways that other instruments are not. Hydrogen is what you find when you look for water. Water is 2 hydrogens and an oxygen, and if ice is present in the surface material, the neutron spectrometer will detect the hydrogen signature. When Messenger turned its neutron spectrometer toward Mercury's polar craters in 2011 and 2012, the signal was unmistakable. Hydrogen was there, in exactly the regions where the Arecibo radar had seen the anomalous bright returns, concentrated in the floors of craters at both poles. Ice, water ice, on Mercury. The question that the discovery answers is not whether the ice is there, but how it survives. And the answer to that is the part of the story that reveals something unexpected about Mercury's geometry. Something that connects to the planet's peculiar relationship with the Sun in a way that makes the ice not just possible, but, once understood, almost inevitable. Mercury's axial tilt is essentially 0. On Earth, the axial tilt is about 23.5 degrees, and that tilt is the reason the seasons exist, the reason that one hemisphere is pointed more directly toward the Sun for part of the year, and the other hemisphere receives the Sun's light at a shallower angle. That tilt means that no location on Earth is permanently in shadow. Even the poles receive sunlight at low angles and with low intensity, but they receive it. On Mars, the tilt is comparable to Earth's, and the same logic applies. But Mercury's axis is tilted by approximately 0.03 degrees. Not 3 degrees, not 0.3 degrees, 0.03 degrees. That is as close to a perfectly upright axis as a real planetary body gets. And the consequence of that near-perfect uprightness is profound. When a planet's axis is vertical relative to its orbital plane, the Sun never rises very high above the horizon at the poles, even on a day when the planet is oriented toward the Sun. The solar light arrives at such a shallow angle, nearly horizontal, that it cannot reach down into the floors of craters that are even moderately deep. The walls of the crater block the light, and Mercury's polar craters are not only deep, but in a place where the Sun skims the horizon at such an extreme angle that crater floors below a certain depth never receive direct sunlight at all. Not once. Not at any point in Mercury's orbit. Not at any point in a year that lasts 88 Earth days. Not at any point in the billions of years that Mercury has existed. These are the permanently shadowed regions, sometimes called cold traps in the planetary science literature, and they are, despite being on a planet baking at 430 degrees Celsius in full daylight, perpetually cold. Cold enough, it turns out, to be colder than many places in the outer solar system. The crater floors in Mercury's permanently shadowed regions, according to the measurements and thermal models informed by messenger data, remain at temperatures below approximately -170 degrees Celsius, perhaps as low as -200 degrees Celsius in the coldest spots. These are temperatures well below the point at which water ice would sublimate away into space, even over billions of years. The thermodynamics are simple. In the absence of sunlight, there is no energy source to warm the ice and drive it off. The crater floor is a thermally isolated pocket, shielded from the sun by its own geometry and by Mercury's refusal to tilt. The ice, once deposited, has essentially nowhere to go, and so it stays. The question of where the ice came from is somewhat less settled than the question of its existence. The most commonly invoked mechanism is impact delivery, comets and volatile-rich asteroids. The kind of small bodies that carry water ice and organic compounds in their interiors have been striking Mercury throughout its history, as they have struck all of the rocky planets of the inner solar system. When such an impactor hits Mercury, the water in it is vaporized on impact, released as gas into the extremely tenuous atmosphere that Mercury barely qualifies as having. Most of that water vapor is quickly lost, broken apart by the sun's radiation or swept away by the solar wind. But some fraction migrates, molecule by molecule, across the surface. And those molecules that happen to find their way into the darkness of a permanently shadowed polar crater eventually freeze and stay there, accumulating over millions and billions of years into the deposits that Messenger detected. Other processes may also contribute. The solar wind itself, a constant stream of charged particles from the sun that bombards Mercury's surface directly in the absence of a thick atmosphere, can drive chemical reactions in the surface minerals that liberate hydrogen, some of which may end up combining with oxygen to form water molecules. These processes are subtle and slow, but Mercury has had a great deal of time, and the cold traps are extraordinarily efficient at preserving whatever water manages to reach them. The deposits that Messenger detected are not uniform across the polar craters, and the variations in their distribution carry information about the history of delivery and preservation. Some craters have ice essentially everywhere their floors are in permanent shadow, others have ice only in parts. And some of the ice deposits are not exposed at the surface at all, but covered by a thin layer of material that Messenger's instruments identified as darker than the surrounding terrain, darker even than the already dark Mercury surface, which is itself one of the darkest solid surfaces in the solar system. That dark covering layer is one of the more intriguing details of the polar ice story, because it connects the ice paradox back to the carbon story. The material covering some of the Mercury polar ice deposits is not ice, it is something darker, and the leading interpretation from Messenger data is that this covering material is carbon-rich, possibly including complex organic molecules of the kind that are found in carbon-rich meteorites and comets. The same impactors that delivered water ice may also have deposited organic material. And while the ice beneath is preserved by the cold, the organic layer at the surface has been processed by the sun's radiation into something darker and more complex. A thin insulating blanket of altered organic material sitting on top of the ice and protecting it from the small amount of thermal radiation that does penetrate into the shadowed regions. Not as direct sunlight, but as infrared heat from the surrounding warm terrain. The dark layer insulates. It is a thin cover that reduces the rate at which heat can reach the ice below, extending the lifetime of the deposits and allowing them to survive in places that might otherwise be just slightly too warm for ice to persist over geological timescales. And the fact that this insulating material may itself be rich in carbon is one of those details that, once noticed, seems to link the different threads of Mercury's story together in ways that feel more than coincidental. A planet whose surface is darkened by graphite, whose deep interior may host a diamond layer born from a carbon-rich magma ocean, whose polar ice is covered by a dark, possibly organic blanket. Carbon, in its various forms, seems to appear at every scale of Mercury's story, from the surface chemistry visible to an orbiting spectrometer down to the proposed crystalline layer hundreds of kilometers beneath the surface. This is not, to be clear, evidence of any single event or any simple explanation. Carbon is among the most common elements in the universe, and its various forms, graphite, diamond, organic compounds, are products of different processes at different temperatures and pressures. The graphite at Mercury's surface is not the same story as the proposed diamond at depth, and neither is the same story as the organic material covering the polar ice. But they are all expressions of a planet that formed in a part of the solar system and under conditions that gave it an unusually high proportion of carbon relative to the rocky inner planets, and that has processed that carbon over 4.5 billion years through every extreme of temperature and pressure that a planetary body can experience. The scale of the polar ice deposits, when you sit with the numbers for a moment, is not easy to picture. Messenger's estimates suggested that the polar regions of Mercury might hold somewhere between 100 billion and 1 trillion tons of water ice. That range is wide because the measurements are indirect and the geometry of the deposits is complex, with ice buried at different depths and in different proportions across dozens of different craters. But even the lower end of that range is an amount of water that would cover a substantial area of the Earth's surface to a significant depth, enough to fill a very large city's water needs for timescales almost too long to contemplate, a quantity of frozen water that has been accumulating, grain by grain and molecule by molecule, over geological time on the surface of a world that by day reaches temperatures hot enough to melt lead. The contrast is not merely ironic, it is physically meaningful. The same feature of Mercury's geometry that makes the polar crater floors permanently frozen, the near-zero axial tilt, is also what makes the day side so extreme, because a planet with no tilt cannot distribute the sun's heat evenly across its surface the way a tilted planet does over the course of its seasons. The poles of a zero-tilt world are permanently in a geometry where sunlight arrives at such a shallow angle that it is spread thin and inefficient, which is why the floors of deep craters there can stay so cold. The equatorial and lower latitude regions of such a world face the sun more directly, at angles that deliver maximum heat. And Mercury's proximity to the sun means that heat arrives with crushing intensity. The same near-zero tilt that preserves the ice also ensures that the sunlit surface receives the full force of the sun's radiation, unmitigated by the seasonal spreading that a tilted planet's geometry would provide. And because Mercury has essentially no atmosphere, there is nothing to carry that heat away from the sunlit side or to retain it on the night side. The temperature difference between a sunlit equatorial rock on Mercury and the floor of a permanently shadowed polar crater measured at the same moment on the same planet is more than 600 degrees Celsius. This is the most extreme temperature range found anywhere on any solid body in the solar system, And it exists not because Mercury is in some exotic location far from ordinary physics, but because its geometry and its chemistry have conspired to create conditions that are, at every turn, more extreme than anything else we can point to among the rocky planets. This is the paradox at the heart of the ice story. It is not, when you follow the physics, actually a paradox at all. It is a logical consequence of tilt, geometry, and proximity to the Sun. But the sequence of logic that leads from the near-zero axial tilt to the existence of ice inside polar craters is not intuitive in the way that, say, the freezing of water in a cold place is intuitive. It requires holding several pieces of planetary geometry in mind simultaneously, requires understanding that shadow can be permanent rather than merely cyclical, requires appreciating that permanence of shadow over billions of years is sufficient to preserve ice even a few tens of millions of kilometers from the Sun. Once those pieces fit together, the ice makes sense. But until they do, the discovery that the hottest surfaced rocky planet has ice hoarded at its poles feels like a trick, like the universe quietly refusing to behave the way you expected. Messenger found the ice in 2011 and 2012, and the findings were published in a set of papers that year and in the years following, filling in the details of where the deposits were, how thick they might be, what was covering them, and what the neutron spectrometer readings implied about the composition. The confirmation built on nearly 2 decades of waiting since the Arecibo radar observations first raised the question, and by the time Messenger's data were in, the picture was clear enough that the debate about whether Mercury has polar ice essentially closed. The question that remained open, and that Bepi Colombo will be in a position to examine in far more detail, is the precise structure of those deposits, their depth profile, the nature of the covering material, and what the full inventory of volatile material at Mercury's poles tells us about the history of delivery and preservation in the inner solar system. Because Mercury's polar ice is not just a curiosity of one unusual planet, it is a record. The same processes that delivered ice to Mercury's cold traps have been operating throughout the inner solar system, and understanding the inventory and history of that ice on Mercury gives planetary scientists a window into questions about how water-bearing material was distributed in the early solar system, how much of it reached the terrestrial planets, and what fate awaited it on surfaces that ranged from permanently frozen polar craters to sun-baked equatorial plains. Mercury's cold traps are, in a sense, archives, preserving in ice the history of volatile delivery to the innermost reaches of the solar system over timescales that no other record could capture. The dark insulating layer over the ice adds another dimension to that archive. The organic rich material, if that is what it is, came from the same population of carbon-bearing impactors that brought the water. Its presence over the ice suggests that the delivery of volatiles to the inner solar system was not just a matter of water, but included a much broader suite of carbon compounds, some of which may have been precursors to the building blocks of biology. This is, admittedly, a very long chain of reasoning from a thin dark layer detected by an orbiting spectrometer, and the organic interpretation of that layer remains a strong inference rather than a certainty. But it is a chain of reasoning that planetary scientists take seriously because Mercury's cold traps, by virtue of their permanence and their low temperatures, are among the best preserved volatile deposits in the inner solar system, and whatever is locked in them carries information that the surfaces of Earth, Venus, and Mars, all much more geologically and atmospherically active, have long since erased or transformed. The ice, then, joins the diamond and the giant core and the still-growing cliffs as one more piece of a portrait that is, taken as a whole, profoundly different from the picture that Mercury's reputation might suggest. A planet described in most introductions as a dead, heavily cratered cinder, the boring small world between the Sun and Venus, turns out on closer inspection to be a world of extremes in almost every direction simultaneously, colder at its poles than many places in the outer solar system, hotter at its equator than the inside of a conventional oven, possibly hosting a diamond shell in its deep interior, definitely harboring billions of tons of ice in its permanently shadowed craters, still shrinking and building cliffs. Still running a magnetic dynamo in a core that should, by the size of this world, have frozen solid long ago. It is a world that has been holding its secrets carefully, releasing them slowly, one spacecraft visit at a time, and the full accounting of what it contains and why it is the way it is has not yet been made. The instruments that could complete that accounting, or at least substantially advance it, are already travelling toward Mercury, already in the middle of their long, looping, gravity-assisted journey inward from the Sun, already close enough in a cosmic sense to their destination that the planet fills a slightly larger angle in their cameras than it did when they left Earth. Bepi Colombo has been in transit since October 2018, and the story of how it is getting to Mercury and what it carries with it to answer the questions this world has been asking for decades belongs to the part of this story that is still unfolding. The part where everything described here, the shrinking radius, the enormous core, the offset dynamo, the diamond hypothesis, the polar ice, the hollows and the scarps, becomes not just a collection of astonishing observations, but a set of questions that a specifically designed instrument suite is, finally, in a position to answer. And so there is one more thing to understand about this world before Bepi Colombo arrives, one more chapter in the record that Messenger assembled during its 4 years in orbit. A chapter that speaks to how violent Mercury's past was and how strange the consequences of that violence remain, embedded in the surface, visible from space, still quietly unfolding in ways that no other world in the solar system quite mirrors. The Caloris Basin sits on one side of Mercury like a scar so large it is difficult to comprehend at first. Difficult to hold in the mind as a single object rather than as a landscape that simply goes on and on in every direction. It is roughly 1,550 kilometers across. To put that in some earthly frame, if you place the Caloris Basin over the continental United States, it would stretch from roughly the Mississippi River to the Pacific coast and cover a substantial portion of what lies between. It is one of the largest confirmed impact structures in the entire solar system, and it was made by something arriving from space so large, so fast, and so violently that the energy released in that single event reshaped not just the ground directly beneath the impact, but the ground on the exact opposite side of the planet. This is the detail that stays with you. The impact that carved Caloris was so energetic that seismic waves propagated outward through and around Mercury's interior, travelling through the rock and the liquid iron and the compressed deep layers, converging from every direction on the single point of the globe directly opposite the impact site, the antipodal point, the far side. The place as distant as it is geometrically possible to be from where the object struck. And when all of those waves arrived, simultaneously, from every direction at once, they collided there in a catastrophic convergence of seismic energy that buckled, churned, and deformed the surface in a way unlike anything that impact normally produces. The terrain at the antipode of Caloris is officially described as chaotic, and that word is precise rather than casual. Hills and ridges and depressions run in every direction, intersecting and overlapping in patterns that do not correspond to any ordinary geological process. No river made these ridges, no glacier carved these basins. They were made by the focused energy of a distant catastrophe, arriving from inside the planet itself, remaking the ground on the far side of a world in the moment of an impact the ground there did not directly experience. Geologists call it the hilly and lineated terrain. The name is straightforward and almost deliberately understated for something so extraordinary. But the understatement is appropriate in a way. It is not dramatic when you are standing in it, if you were standing in it, because it is just terrain, hills and linear features, rising and falling, running in directions that make no particular sense if you do not know the history. The drama is entirely in the causation, in the invisible seismic thread that connects these quiet hills on one side of Mercury to the enormous scarred basin on the other, a thread that runs through the interior of a planet and arrives 1,500 kilometers away, carrying enough energy to fundamentally reorganize the surface. Caloris itself is ringed by mountains that rose in the rebound of the impact. Peaks pushed upward by the recoil of crust that had been compressed and then sprung back. Inside the basin, the floor has been flooded with volcanic material, smoothed over in the long aftermath of the impact, and then fractured again as Mercury continued to contract and the floor of the basin experienced its own subsequent deformation. The fractures on the Caloris floor run in patterns that reflect both the original circular geometry of the impact and the later compressional forces of the shrinking planet, so the basin is itself a record of two different eras of planetary stress, layered on top of each other, readable by the instruments of spacecraft that know what to look for. It is, in a sense, a compression of Mercury's entire story into a single structure: the violent youth, the volcanic flooding, the subsequent shrinking, the fracturing that followed, all of it visible from orbit. And then there are the hollows. Messenger discovered them, and they were not expected. Nobody had predicted them, nobody had modelled their existence before the spacecraft arrived. And when the first images came back from orbit and the team began to study the surface in systematic detail, these features appeared and did not immediately fit any category that planetary scientists had developed from studying other worlds. They are shallow, irregular depressions, brighter than the surrounding surface, with flat floors and scalloped edges. And they occur in clusters across Mercury's surface, often concentrated inside craters or on slopes. Sometimes in fields of many hundreds or thousands of individual pits that together cover significant areas. What makes the hollows extraordinary is not just their appearance, but what they appear to be doing. The leading interpretation, the one that fits best with what Messenger measured and observed, is that they are actively forming. Right now, material on Mercury's surface, under the unfiltered bombardment of solar radiation and solar wind particles and the hard vacuum environment of a world with essentially no atmosphere, is being removed. Volatile compounds, materials that would be stable underground or on a world with some protective covering, are sublimating, escaping directly from solid to gas and then dispersing into space. And where that process occurs, the surface is left hollow, literally pitted, a shallow depression where something used to be and is no longer. The bright floors are fresh exposures, surfaces that have not yet had time to accumulate the darkening patina that the rest of Mercury's surface wears, and their brightness is the brightness of youth, of recent exposure, of geological processes that are still in progress. This is Mercury being actively reshaped by its environment in real time. Not just by the slow contraction from inside, not just by ancient impacts from outside, but by the continuous stripping action of the sun itself, removing material from the surface grain by grain, pit by pit, hollow by hollow, across an unknown timescale that may extend to today. The hollows suggest a surface that is more dynamic than it looks, more changeable than the ancient cratered crust implies, a world where the sun's proximity is not just a temperature fact, but an active geological agent, reaching down to the ground and slowly taking it apart. Messenger found all of this. Over 4 years in orbit, from the moment it slipped into Mercury's gravity in March of 2011 to the final months of its mission in 2015, the spacecraft mapped the entire surface, measured the magnetic field in detail, counted the neutrons bouncing off the polar craters to detect the ice hidden inside them, analyzed the elemental composition of the surface with its X-ray and gamma-ray spectrometers, and built up a picture of Mercury that was richer and stranger and more internally contradictory than anything the mission planners had anticipated when they first pointed the spacecraft at this small, dense, difficult world. But Messenger was running out of fuel. Spacecraft carry finite propellant and the task of maintaining an orbit around Mercury, fighting the relentless gravitational and radiation pressure in the inner solar system, slowly depleted what the mission had carried. By early 2015, the team was performing increasingly creative maneuvers to extend the mission, using the helium pressurant that remained in the tanks after the actual propellant was exhausted to make tiny adjustments that bought weeks of additional science. They kept the spacecraft alive longer than anyone had expected. But eventually, the fuel was truly gone, and there was nothing more to do but let orbital mechanics take over. On the 30th of April 2015, Messenger impacted the surface of Mercury at roughly 3 kilometers per second. It was not a failure. It was the planned end. A spacecraft that had travelled billions of kilometres, that had been the first artificial object to orbit the closest planet to the Sun, that had returned the most detailed and comprehensive scientific data set Mercury had ever yielded, hit the ground in the northern hemisphere and created a small new crater, adding one more mark to a surface already saturated with the records of impacts over 4 billion years. The crater it made is tiny by Mercurian standards. But it is there, and it is permanent, and in a sense it belongs to the surface now. Another piece of the geological record, another feature that future instruments might image and study, another small fact about a world that is full of them. The knowledge that Messenger left behind was extraordinary and incomplete at the same time. This is always how it is with planetary science. Every mission answers some questions definitively and opens new ones that the mission's instruments were not designed to resolve, or could not resolve with the technology available when the spacecraft was built and launched. The giant core and its liquid outer layer were confirmed. The weak, offset magnetic field was mapped in detail. The carbon-rich surface was measured. The polar ice was found and characterized. The Lobate Scarps were counted and catalogued. The young, crisp faults suggesting ongoing contraction were identified. The hollows were discovered. The colorous antipodal terrain was imaged at high resolution. But the deep interior, the core-mantle boundary, the question of exactly how the dynamo sustains itself in a body this small, the question of whether the carbon in the surface connects to a diamond layer below, the question of whether any of the scarps are presently active in a seismically detectable sense. These questions could not be answered by messenger alone, with the instruments it carried, with the time it had. What was needed was a successor. What was needed was a mission designed with Mercury's specific mysteries in mind. A mission that could carry instruments targeted at the unanswered questions. A mission that could approach Mercury's interior not just from the surface record and the gravity field, but from a multispectral, multi-instrument, multi-orbiter approach that covered the magnetosphere and the surface and the interior. Simultaneously, in a way that no single spacecraft mission could achieve. Bepi Colombo is that mission. And the name itself carries a piece of the story. Giuseppe Colombo was an Italian mathematician and engineer who worked in Padua and who in the 1960s and 1970s made two contributions to planetary science that bear directly on Mercury and on the mission named in his honor. The first was the theoretical explanation of Mercury's 3-2 spin-orbit resonance, the strange and counterintuitive configuration in which Mercury rotates exactly 3 times for every 2 orbits it completes, a relationship that Colombo worked out from the mathematics of the gravitational interaction between the planet and the Sun. Before his work, astronomers had believed Mercury was tidally locked in a 1-1 resonance, always showing the same face to the Sun, the way the Moon always shows the same face to Earth. Colombo showed that the 3-2 configuration was the actual state, and his analysis was correct. The second contribution was the concept of using gravity assist maneuvers to help spacecraft reach difficult destinations in the inner solar system. When NASA was planning the Mariner 10 mission in the early 1970s, Colombo calculated the trajectory that would allow the spacecraft to fly past Venus, use Venus's gravity to redirect its path toward Mercury, and then return to Mercury multiple times. Each return timed to coincide with the spacecraft's own orbital period around the Sun. His insight gave Mariner 10 3 Mercury encounters instead of 1. He died in 1984, but the trajectory technique he developed became the foundation for how humanity would continue to reach the inner planets, and the spacecraft that is now completing a far more elaborate version of exactly this kind of journey carries his nickname, the name his friends used, Bepi. Bepi Colombo launched on the 20th of October 2018 from the Guyana Space Center at Kourou. It is a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, which makes it one of the few deep space planetary missions undertaken by 2 major space agencies as co-equal partners, each contributing a major spacecraft component and a set of scientific instruments. What they launched was not 1 orbiter, but 2, stacked together for the journey, riding as a single combined stack until they reach Mercury and separate to enter independent orbits around the planet. The European contribution is the Mercury Planetary Orbiter, the EMPO, which will settle into a relatively close orbit around Mercury and focus on the surface and interior, mapping the geology, measuring the gravitational field with precision, studying the mineralogy and elemental composition of the crust, and searching for evidence of ongoing tectonic activity. The Japanese contribution is the Mercury Magnetospheric Orbiter, known as MEO, which will orbit at greater distances and focus on the space environment around Mercury, the magnetosphere, the exosphere, the interaction between the planet's weak magnetic field and the intense solar wind that bathes this inner part of the solar system. Together, the 2 orbiters will study Mercury from the inside out and the outside in simultaneously, which is not something any previous Mercury mission could do. But getting there has required patience on a scale that is difficult to appreciate without understanding what it means to travel toward the Sun. The intuition most people carry about space travel is that going somewhere closer to the Sun should be easier than going somewhere farther away. The Sun is pulling everything toward it. After all, surely sliding inward is like going downhill. And in terms of gravitational potential energy, that intuition is correct. But in orbital mechanics, the challenge is not potential energy alone. It is velocity. A spacecraft in orbit around the Sun is moving at a speed determined by its distance from the Sun, and Mercury's orbit is much closer to the Sun than Earth's, which means Mercury moves much faster than Earth does in its own orbit. To reach Mercury and actually slow down enough to be captured by its gravity and enter orbit, a spacecraft launched from Earth must shed an enormous amount of orbital velocity. It must slow itself relative to Mercury. And slowing down in space requires fuel, just as speeding up does. The thrust needed to break from an Earth departure trajectory all the way down to Mercury orbit velocity would require more propellant than any practical spacecraft can carry. The solution is the same one Giuseppe Colombo helped pioneer: use the gravity of other planets to do the work that fuel cannot. Fly past Earth and let Earth's gravity bend the trajectory and adjust the velocity. Fly past Venus twice and let Venus do the same. Then fly past Mercury itself 6 times, each flyby further shedding orbital energy. Each pass using the planet's gravity to slow the spacecraft incrementally until the velocity gap between the spacecraft and Mercury's orbit is small enough for the onboard propulsion system to close. 9 planetary flybys in total. 1 of Earth, 2 of Venus, 6 of Mercury, strung across 7 years of flight, each precisely calculated, each arriving at the right point in space at the right moment to extract exactly the velocity change needed for the next leg. The margin for error is vanishingly small. These are not approximations. They are exact, and the spacecraft is on a trajectory that was calculated and refined over years of careful planning, and then refined further as the actual measurements of its position in space were compared against the predictions, and corrections were made, tiny firings of the ion thruster in the long, quiet stretches between flybys, nudging the path by fractions of a millimeter per second to ensure the next planetary encounter arrives on schedule. The propulsion system that allows those corrections and that provides the low-thrust continuous push that has helped shape the trajectory across the inner solar system is a solar electric ion drive. It works by using power from the solar panels, which are large and efficient this close to the Sun, to ionize xenon gas and accelerate the ions to very high velocity out of the back of the spacecraft. The thrust produced is tiny compared to a chemical rocket, far too small to feel, far too small to be visible as a flame or a plume. But it is continuous, it runs for weeks and months at a time, and the accumulated effect of that gentle, unceasing push adds up across the long transit of the inner solar system, shaping the path in ways that conventional propulsion could not sustain. Bepi Colombo has been flying since October 2018. It performed its Earth flyby in April 2020, its first Venus flyby in October 2020, its second Venus flyby in August 2021. And then, beginning in October 2021, it began its series of Mercury encounters, the 6 close passes that would gradually reduce its velocity relative to the planet until the spacecraft was finally slow enough to be captured. Each Mercury flyby returned images. Each pass offered a preview of the surface that Messenger had mapped in such detail. Each encounter tested the instruments and refined the spacecraft's position in space.